Hey everyone, Joe Grant here to give you a demonstration and introduction to the JTAGulator. The JTAGulator is an open source hardware hacking tool that I designed last year and have just come up with a bunch of firmware updates that will basically let you identify on-chip debug interfaces on unknown circuit boards. So you basically have 24 channels that you can connect up to 24 unknown points of a circuit board, and the system will enumerate through all the different pin permutations to identify JTAG interfaces, which are low-level programming debugging interface, or asynchronous serial or UART interfaces that are commonly used for root shells and debug access to embedded systems and things like that. So it's a really handy board. I'll give you a little bit of rundown of the board here, and then we'll do a little demonstration of the different features. So everything is handled through the USB interface. When you plug in the device to a PC, we have an FTDI FT232 part, a standard USB to serial interface. So on your computer, you're going to see a virtual COM port show up, and it's a cross-platform tool, so you can use it, with whatever terminal program you want on whatever platform you're using. So we get power through the USB port. We also have our user interface, command interface through that port, and we can also upload new firmware to the Parallax propeller processor, which is the heart of the JTAGulator. So as I come up with new code, which is pushed up to GitHub, you can grab that using standard propeller development tools through mini USB to program new code. So that's really handy. Some other features of the board. Down here we have a op amp, and this serves as a single bit digital to analog converter that we're using to adjust the target voltage of our system, which I'll get into more detail of a little bit later. We have another device up here, a double EEPROM that stores our program code. We have some level translators that are going to use the target system voltage and translate the voltage levels between the 3.3 volts of the Parallax propeller processor to whatever our target system is, which is, we have a range of 1.2 to 3.3 volts. Then we have some resistor networks here, some current limiting resistors that are used just to protect the interface between the JTAGulator and the target board. We have a bunch of diodes that are used as diode clamps to protect against overvoltage and undervoltage, because we never really know what we're connecting to on the target circuit board. So let's actually hook this thing up, give you the demonstration of how it works. The first thing we actually need to do before connecting anything is figure out a ground connection of the target board. So what I'm using here for the demonstration is a Linksys WRT 54G version 2. It has DD-WRT loaded onto it, and we need to find a ground connection, which is or a ground point, which is going to be used as our 0-volt reference. And when you connect different electronic devices together, you need to have some sort of shared voltage reference, so the signals can communicate properly and you have a good electrical connection. So we need to figure out what the ground point is so we can connect it to the JTAGulator. So we usually want to do that when the target board is off. And what we can do is take a multimeter, standard multimeter. It's a very simple test, and you set your multimeter to a continuity mode. So let my fluke meter power up. Go into the continuity mode. So now when I touch the probes together, if there's a short circuit or a connection between a connection below some resistance value, maybe it's 100 ohms or something like that, we'll get a beep. So to find the ground connection on our board, I'm going to hook up to a known ground point on this particular board, and a very common ground point on any board is going to be for the power input. So I'm hooked up to the side of this power plug here, but I want to find an easier ground connection, and usually that's going to be on one of the connectors that I'm interested in. So in this case, there's two connection headers here. I've actually soldered these connections in, and these are male headers, but normally when you open up a circuit board, you're not going to see headers soldered in. If you do, you're really lucky, but usually you would see something more like on this board where you just have this 2x5 row header but no connector there, so you just see these test points here. But that's a pretty good indication when you see something like that. It's like, all right, maybe that's an interface that we want to go after and try to figure out the pin out and see what it is. So in our case, I've already soldered on these connectors, so it's going to be a little bit easier to kind of probe stuff. So what I'm going to do is I'm in continuity mode. I'm just going to go across each of the pins and see if there's a connection. And we heard that first pin had a connection there. So now I know that there's a connection from one pin on the connector to ground, and that's the one I'm going to use to actually connect up to the JTAGulator. So I'm going to remove my multimeter, take one of my female to female probes and connect it up from the ground connection on the target board to my ground connection on one of my 2x5 row headers. Now with the JTAGulator, we have these terminal blocks, little terminal screw blocks along here that you can connect wires up to connect to test points or connect to connectors. And you also have these 2x5 row headers, which can be used with a bus pirate cable. So instead of wiring individual connectors, the bus pirate cable is used with the bus pirate, which is a very useful tool for interfacing with serial devices and some other hardware hacking stuff. Super cheap, you can get these all over the place. So if you use this, all you have to do, instead of wiring individual wires, you can actually just plug it in to one of the 2x5 row headers, and now you have all of your connectors here, your ground connection can clip on, and then your different test leads that you can clip on as well. So there's a few different ways you can connect up to the target device. So now we've identified our ground connection. What I'm going to do is plug in our target. I'm going to plug in the JTAGulator. Things are going to get powered up. And as this is getting powered up, what we can do is start connecting up some of the pins that we're interested in. So the way that JTAGulator works is that we're basically taking a bunch of channels connecting up to our unknown test points on a board, and it's going to go through different permutations of the different pin permutations to identify the right pin out. So what I'm going to do is I have a bunch of female to female wires. I'm going to connect up. Our first demonstration is going to be with JTAG, so we're going to be on this connector here. And this particular board is really nice because it has JTAG and it has the asynchronous serial UART interface. So I'll do the demonstration on JTAG first. And what I'm going to do is just take, starting at channel 0, just take my wires and just connect them up to some pins of the board. The ones that I think might be the JTAG interface. And it doesn't matter what order you plug them in or anything. I just start at channel 0 and then go channel 1, channel 2. But on this connector, you know, I can put this one over here. It doesn't really matter. And to save time and to save wiring, I'm only doing the top row because I know that that's where the JTAG interface is, but I don't actually know what the pinout is. And that's really what we're looking for. And the goal is once we find the pinout, then we can use other off-the-shelf JTAG tools to start manipulating with the device. All right, so here we go, the final connection. Plug this in right in the middle. I made this hard for myself because I did all of the outside pins first. Okay, so now we have the JTAGulator hooked up, and we have all of the pins from the JTAGulator going to the unknown test points on our Linksys WRT54G, which is going to be JTAG. So everything's connected through USB. Now we can go over to my machine, which I'm running HyperTerminal on Windows XP. Again, this is a cross-platform tool. It's going to show up as a virtual COM port on whatever system you're running. So what we can do is we're going to enable our COM port. Now when the JTAGulator is reset or first powered on, we're going to see this awesome ASCII art JTAGulator logo come up because every product needs to have awesome ASCII art. And it says, welcome to JTAGulator. Press H for available commands, so we can do that. Press H. We see all of our commands, at least currently for version 1.2.1, split up into JTAG, UART, and then the general commands. One of the new features I've added for this firmware version, we hit H to display version information. Or sorry, we hit J. We see firmware 1.2.1. All of the code, this is an open source project as I mentioned, so all the code, hardware designs, everything, documentation, all that stuff is online. If you go to jtagulator.com, that's going to redirect to my website with all the information. GitHub has the actual source code and my to-do list and some other stuff. I'm very proud that I actually learned how to use GitHub, at least enough to host this project. And then support is handled by Parallax, and they manufacture the Parallax propeller processor and do a bunch of hobbyist robotics and electronic stuff. And I've worked with them for a long time and figured, okay, they're going to do the manufacturing and distribution and handle sort of the basic support, so I can focus on doing development of the tool and developing other things. Of course, if there's complex problems, they're going to end up coming to me. But going through that support link first is going to be the best way to get answers. So, okay, we have the version information that we need. First thing we need to do is set the target system voltage, which, as I mentioned, we can range from 1.2 to 3.3 volts, but we need to figure out what that is. So in our case, we're going to need to use the multimeter with our target board and do some measurements, kind of probe around to figure out what the best or most likely system voltage is. So let's go back over to our board. I'm going to set my multimeter to standard DC voltage measurement. And I know that we have our ground connection is on one of these pins, but I'm just going to hold it up to the power port because that's easier. And then to find the target system voltage, there's a bunch of different ways to do it. One of them is you can just poke around randomly on the board. You can identify major parts, like this Broadcom chip is probably the one that we're going to be interfacing with. So we can maybe try to find the data sheet for that, see what it says for target system. But what I like to do is just look at the connector itself, and at least the target connector that I'm interested in, and just take measurements on all the different pins and see if there's any that are a likely system voltage. So I'm moving around mostly 0 volts. Now I see one here that's 3.3 volts, and that's a standard system voltage. Sometimes like a mobile phone might be 1.8 volts, there might be other ones. And you can just probe around on the board and see if there's any that are higher, any that are lower. But 3.3 volts is the one. So that's our target system voltage. And if we're measuring one that isn't the right one, we'd see 0 or maybe some other voltage. So 3.3 is the target system voltage. So now that we know that, we can go to the V command, enter target voltage 3.3, new target voltage set, and now we're good to go. Now we're ready to actually start the JTAGulator process. So the first thing we're going to do, there's a few different ways to identify JTAG pinouts. And JTAG is this industry standard interface that basically defines this low-level interface. It doesn't talk about any kind of high-level stuff that you can do with the chip. It basically defines this simple state machine that I like to think of it as like a simple kind of CPU that you basically are shifting data in and shifting data out in different modes. So it's a very low-level spec, but there's a few different things that we can take advantage of to try to identify the pinout. And the cool thing about JTAG is it's sort of this Achilles heel of embedded systems, and it's something that attackers go to all the time because it gives you direct access to hardware. It will let you twiddle all of the pins of the actual device if you can get access through the JTAG port. So you're sort of like this puppet master controlling all of the pins. And if you can control the pins of the CPU, then you can control the pins of everything that CPU is connected to. So external memory, maybe other peripherals. Vendors also will build in their own support over JTAG for other things, like programming internal flash memory, or extracting internal flash memory, or doing debug, so single stepping and stuff like that. And a lot of that is going to be abstracted from us, but we can either take advantage of like a legitimate development environment, or maybe some open source JTAG tools like OpenOCD to start manipulating with the devices. So there's really a lot you can do with JTAG, and vendors know that it's an issue, and engineers know that it's an issue, but legitimate design engineers need it, legitimate manufacturers need it, and as hackers, we can take advantage of that and look for those ports and find them. So there's two different ways that we're going to identify the interface. The first one is with an ID code scan, and the second one is with a bypass scan. The ID code scan is faster, so we do that one first. That's going to give us 3 of the required pins of JTAG, and not the 4th one. So it's a faster scan, but doesn't give us the full pinout. JTAG actually has 5 pins. 4 of them are required per the spec. 1 of them is optional, and the optional one is the test reset pin, which is actually used by vendors a lot of times. It's an active low pin, and vendors will use it on their boards to try to disable JTAG, or they will disable JTAG. So if you don't know the test reset pin, but you know the other pins, the JTAG is still going to be disabled. So we need to find that test reset pin so we can pull it high to enable the JTAG port. So that's an optional one, but usually it's used, so we want to still find that, which we will do with both scans. But the ID code is much faster. So we're going to do ID code scan first, and then we'll do bypass scan, which looks for the other pin. So let's take a look. So first thing we're going to do is I for ID code scan, and we have 6 channels hooked up, channels 0 through channel 5, which we just arbitrarily connected up to the connector. 120 possible permutations, spacebar to begin. Press spacebar, and pretty much right away it says JTAGulating. Pretty much right away we see a response. TDI is data in, not applicable because we're not looking for that pin coming in. TDO is data out. TCK is clock. TMS is mode select, which we use to step through the state machine, different states. And then T reset is the test reset pin. Now what we're doing for ID code is basically when the state machine of JTAG, or the tap interface of JTAG, is reset, if there's an ID code available, it's going to be in the data register. So what we're basically doing is setting a number of pins, a certain pin permutation, trying to shift data out of what we think might be the data register. And if we see something that corresponds to an ID code, we'll print that out on the screen. Or we'll actually list the potential pin out. And we'll try different pin permutations and try to read an ID code. And an ID code, as you'll see, is actually a very, very useful piece of information because it's unique to a particular part on a board. So if we're able to get access to an ID code, even if the part numbers are scraped off the board, or if it's maybe if the part is covered by epoxy, or maybe there's multiple dies within a single chip, so we can't identify which things are what visually from the board. The ID code is going to give us information that we can then go do Google searches and research to find other information about the part. So it's really useful. So all right, so ID code, we already have our pin out here. Now what we can do is get the ID code, which I've set up as a separate command. So just to show you the command list again, get device ID is D. TDI isn't needed, so TDO is pin 4. TCK is pin 1. TMS is pin 5. One device in the chain, which is the standard. The ID code scan doesn't actually tell you how many devices there are in the chain. The bypass scan will, but in our case we know it's one device in the chain. Hit enter, and now we're reading the ID code. So this is the actual code being returned by the target chip on our Linksys board, the 1471217F. So if we went and did a Google search on that, we'd find out that it's a Broadcom BCM 4712. This board has been hacked to death. There's tons of information about it online. And we would then, be able to get the boundary scan information and other information that we might need to start manipulating the part. I've also parsed out, this is a new feature for this version as well, parsed out the device ID to the specification that actually shows manufacturer ID, part number, and version number, so that will just give you more information. Manufacturer ID here, 0BF, is not always used the right way, but sometimes it is. And the manufacturer ID is actually a JTAG assigned number given by the JTAG standard body. So you should be able to go and look up this number in the JTAG document for device IDs of JTAG, and it will tell you, like, this is Broadcom, 0BF is Broadcom, or whatever the company is. So that will give you more information for reverse engineer. So that's ID code, but we need to find that extra pin. We need to find TDI. And the way to do that is a slightly longer test, because the process is just longer, is bypass. So we'll go to B. Number of channels still is 6 channels. Now we have more permutations because we're looking at more pins, because now we need 4 pins instead of 3, plus the reset pin. And we'll do spacebar to begin. So another new feature is we actually have a little indicator here to show that we're JTAGulating. And then you can go down to the board itself, and the indicator here, the LED, is actually blinking. So now we know that it's actually doing a search. And when it's done, that LED will turn green. So the way that the bypass scan works is bypass is a required command from required command of JTAG. So no matter what the device is, it needs to have bypass mode. And what that does is basically the chip is going to take in data on data in and pass it to data out. Basically like playing operators, just passing the data along through a single 1-bit register. So that's a required command, and the opcode to that, to force a device into bypass mode, is sending all 1s into the instruction register. So we can take advantage of that by setting our pins to what we think might be the right permutation, shifting a bunch of 1s into what we think might be the instruction register, and if we do enable bypass mode, we send in data on data in. look on what we think might be data out, compare them, and if it matches, then we have a pretty good indication that that's a good set of JTAG pinouts. So the bypass mode actually just completed, so we can take a look here, and now we see TDI is pin 3. All the others should be the same because nothing else has changed. So we have TDI pin 3, TDO pin 4, TCK pin 1, TMS pin 5, TRSIT pin 2, number of devices detected 1. So if we had multiple devices in the JTAG chain, which is something that JTAG can do, which is very cool, so you have a single interface that you can then communicate with multiple devices, we would see different devices here, and then we would get different ID codes as well. So here's our full pinout, 3415. We can verify that by doing the test bypass command, which is T. So now it's going to say enter new pin, so 3415, one device in the chain. Now we're sending in a random 32-bit string on TDI and then looking at it on TDO. So now we know that the data we're sending in is right, the data we're sending out is right, it matches, great. Now we know our pinout is good. I can do that again. When you hit enter, it remembers the value that you just used. It's just a little faster. Different 32-bit random string, and still a match. So there we go. Now we have the full JTAG pinout of the device. Now, one thing I do want to do with the JTAGulator that I haven't implemented yet is support for OpenOCD. So right now, at this point, once you find the JTAG pinout, you have to disconnect everything from the JTAGulator, get some other JTAG hardware, maybe like a bus blaster. I think I have here. Yeah, this is the bus blaster by Dangerous Prototypes. Really cool open source JTAG interface. All sorts of other ones. Here's a Sager J-Link. So there's all sorts of other tools, hardware tools that you can use, hardware interfaces that you can use to then start manipulating with the target hardware that you've just identified the pinout. So the goal is to add OpenOCD support to the JTAGulator so you can leave everything connected and then start doing stuff. So maybe you want to extract memory, maybe you want a single step, maybe you want to do something else. That's the goal. But for now, you still need to have some extra hardware. So that's JTAG. Let's go back over to the board. What we're going to do now is move everything over and try to find the UART interface, this asynchronous serial interface that is very commonly used, especially on embedded systems and on Linux-based devices, as you'll see. So I'm going to leave all the connections the same on the JTAGulator side, unplug all the pins from JTAG, and this particular board has two serial interfaces, port 1 and port 2. We're just going to connect up to port 1 because I know that that's there, and just again arbitrarily hook up these wires. It doesn't matter how I plug them in, but I'll at least do them in order this time so it's easier to plug them in. So this particular port is smaller than the JTAG port. So we have a few leftover pins. I can just take these out of the JTAGulator. We don't need those. And with UART, what we're looking for is TX and RX. Now the UART interface usually has a bunch of other control signals as well that we don't really use anymore. You don't see them a lot on boards. But the main ones are TX, which is transmit, RX, which is receive. And then, of course, we still need our ground connection, our shared 0-volt reference. So we're basically, in this mode, what we're going to do is just send in a user-defined string of a default carriage return, but maybe you have a feeling the target system needs like a control sequence or +++ or something else. You can enter that in, and the board is basically going to set the pin permutations, send that user string, and look for a response at a bunch of different baud rates that are defined in the firmware as like a table lookup. So let's take a look over on the screen. We already have our target voltage set from our JTAG test, and now we're just going to use the U command, which is identify UART. Enter text string, so here we're just going to use the default of carriage return. Number of channels, so now we have channels 0 through 3, so we have 4 channels hooked up. 12 possible permutations, hit spacebar, and now we wait. And then we get a bunch of different responses back. Now this is good. because what we see here is a bunch of responses at different baud rates, but the TX and RX are all the same. So that's telling us that we're able to send data on pin 3, on channel 3, TX, and receive data on pin 1. But what the JTAGulator doesn't know is which data is valid, because it can't discriminate. It doesn't want to discriminate, because then it might eliminate something that is a possible baud rate. So the human needs to actually go through the list and look and see if there's something that it might be, because the interface might not necessarily be printable ASCII, right? It might be some other bytes. But in our case, we have an actual printable ASCII interface, so it's going to make it a little bit easier. We go through, we see 57.6 is a 0D carriage return. That could be useful. Scroll down a little bit more. Here's a baud rate at 115.2, 0D, 0A, carriage return line feed. So that seems like that would be the most likely interface. What we can do now, as opposed to with JTAG where we'd have to unplug everything and connect up new hardware, we can do a pass-through mode of the JTAGulator, which will actually let us communicate directly with the target board. So anything that we type on our keyboard is going to be sent, level translated, and then sent over to the target board. So let's go ahead and try that. P for pass-through. TX is pin 3. RX is pin 1. Baud rate 115.200. Enable local echo. This is a new feature as well. Most of the time, the target board is going to control whether or not it wants to echo characters back. So by default, we're going to say no, but sometimes you might want to enable that. So I'll just hit enter. Now we're in UART pass-through. So now I can actually hit things, hit keys on my keyboard, and here we see DDWRT login, which is awesome. So let's log in as root, default password admin. Now we see we're in, we got a root shell, we can do all sorts of stuff and mess around with the device. Once we're done with that, we hit Control X, UART pass-through complete, and now we're back in JTAGulator mode. So those are the two interfaces right now that we're able to do with the JTAGulator, JTAG and UART. As I mentioned, I have a ton of other things I want to add to the project, so check out the GitHub repo, check out my website. Feel free to contact me with bug fixes and feature requests, and if you want to start working on the project or contribute to the project, that would be great. It's just a very cool general purpose tool that is just a great hardware hacking tool to identify interfaces. So that's the current demo. Stay tuned for more, and I'm Joe Grand signing off. JTAGulation successful.